Hello everybody, this video will be about tracing C function Fopen, and in this first part of video I'll be focusing on IDA free user mode walkthrough tracing to NTApi. You can see that the second part of the video will be focusing on usage of Windows debugger for kernel debugging and walking through user mode to kernel executive subsystem. And as you can expect, it will be more advanced because we will be doing something like walking through some kind of wall between user mode and kernel mode. It's as I said already, it's more advanced, so I would like to let it be for later and come back to the first part. As you can see, I chose to use the IDA free because I want to show you that IDA free has already very powerful built-in features like function tracing and instruction tracing, local Windows local debugging, and other stuff. And also, I expect that most of you guys don't have available the IDA Pro version, so I chose to use IDA free. There is another reason why I chose to use IDA free, and it's because this tweet from Ilfak, and basically this tweet says IDA Freeware will come bundled with a free x64 decompiler soon. So basically this tweet says, hey man, stay tuned because something big is happening. Okay, so let's jump back, and in this video I'll be covering the Fopen.exe file, which is an executable file, which basically will be performing the calling the Fopen C function, which goes to the ucrt base DLL, which is a C runtime DLL, and it follows the some execution flow, which goes and ends in the ntdll.dll-NtCreateFile, which is the last one in the user mode. After that, the system call or sysenter occurs. Basically, what does it mean? It means that the execution is transferred to the kernel executive subsystem. But this is not a part of this first part video because we can debug only the user mode with the user mode debugger. It will be covered in the second part. Okay, first of all, I want to show you the source code of the Fopen.exe file, which will be used here. Well, we can jump to the Visual Studio, and you can see that it's really basic code here. You can see that only fopen and fclose C function are implemented. You can see that fopen basically what fopen does. It creates a new file which name is here, and it will create it in mode write. Basically, if the file doesn't exist, it creates new ones, and if the file exists, already exists, it will obtain the handle to the file, and you will have the right access to the file after obtaining the handle. In this case, it will be creating the new file because the file doesn't exist. For now, we can jump to our VM. I would like to switch to the full screen. It will be better for you. And you can see that I already prepared here IDA free and Fopen.exe, the assembly code of the Fopen.exe you will see later. First of all, when we jump to the IDA free, we have to check one really important thing in the environment variable. So jump to the environment variable and check that you have properly set the NT's symbol path. Basically, what does it mean? It's needed for the IDA for downloading the debug symbol file for some DLL, Microsoft DLL, and to apply the symbols to our code. Basically, it will download the symbol file from the Microsoft domain and save it to the symbols directory in C partition. So I have already prepared the environment variable, so we can jump to the IDA free. Okay. I don't want to apply the PDB file of the fopen.exe, so no. Well, and where we are now, if you want to see the location in the graph view, you can go to the option, general, and line prefixes. Okay, and you have here 401275. And if you go back, you can open it in, for example, CFF Explorer and go to the optional header, and entry point here should be, yeah, entry point 1275, and the image base is 0040000 and 1275. If you jump back to the IDA, 1275 is the entry point. So we end on the entry point of this fopen.exe file, and we want to find the main function, as you saw in the source code in Visual Studio. How you can find the main function? Basically, you can go to the end of this graph view, and somewhere in the end of this graph view there should be some call to function which is returning some value, and you can see that here is the argument value, argument count, and here is some call, and this call is returning value in EAX register. So this looks very suspicious for our main function. Let's jump to it, because you can see that after this it goes to the exit, or it goes to the exit. So, or it goes here. Yep, this looks suspicious. Let's jump to it. And what we got here? Yep, it's I'm 100% sure that it's our main function. So let's name it as a main. Press N and name it as main. Okay, and you can see that the proper type was applied. You can see here the call to fopen and fclose, basically what we saw in the source code in Visual Studio. First of all, I want to show you we can use the local Windows debugger, which is available in the free version of IDA. So it's really good for us. And I want to put a breakpoint here. First one. And put a breakpoint here because I want to trace the execution of the fopen function. Let's start new process. Yes, it's a warning that you will be debugging the fopen.exe in local host. So yes. Okay, what we got here? Yeah, the breakpoint was hit. And basically I really don't like this kind of Windows structure, so I want to modify it simple. So I want to close this one. This one could be quite smaller. The stack window could be like this. I don't need the thread window. I need the module window, but I want it to be here. This should be like this. Okay, and I want to see the stack trace. So go to the debugger and debug window and stack trace, and put a stack trace somewhere here. Yep, and it's something like that. This really suits me quite well, so I want to save it. Okay, with this I'm quite satisfied. And if you want to save it and want to use it whenever you want, just go to the window and save desktop. And I will choose the default one and OK. This is very useful because, for example, if you modify it like this, and you can, for example, jump back and quite do some modification here. For example, you can made it bigger, and so here, and you have something like this, and this is not what we want. You can basically go to the again to the window and load desktop, and we already saved the desktop we wanted in the default debugger. So press OK, and what we got? This one, which suits me the best. So okay, let's continue. So we are debugging the fopen.exe. We are in this position, and after that it will be performing the call to the fopen function. If you jump to the fopen function, you can see that fopen goes to the here. If you go to the text view, you can see that it's a part of UCRT based DLL, which is a C runtime DLL. You can go switch back to the graph view, and what is here? Some call to something which is unknown. It's not recognized as a function. It's not recognized as a code. It's undefined, some bytes. So it's basically because this module is in memory and it hasn't been already analyzed. So if you want to analyze, I will show you how to do it. We need something more than analyzing these modules. Go to the modules window, and what we need, first of all, mark this module. Basically, we need the ntdll.32, ntdll, kernel32, kernel base, UCRT base, which is somewhere, yeah, UCRT base, and that's all what we need. Right click on mouse and load debug symbols. What it does, it basically contacts the Microsoft server and try to download the debug symbols for these Microsoft libraries and try to apply the debug symbols. The debug symbols contains information like proper names of function of the libraries, proper types, proper names of variables, some information related to stack, and other really useful information. So we need to download it and apply it. You can see here that IDA is performing some applying the debug symbols. You can see it here too. And with that, we want to also to recognize the, as you already saw, some function are not recognized as a code or as a functions. So we want to analyze this module in memory. We want to analyze these modules where we applied already debug symbols. So again, right click on these modules and analyze module. Yes. This will take some time because it's really, I don't know how to say it. The AI is performing the analysis of this module. I mark and press the analyze module, and it will recognize all functions, all code as a code and other stuff. So it will be more useful for our purpose. So let's jump back to the debug view. You can see the analysis is running. Still, you can see here some arrow which is doing the analysis. And what we got, what we want to next is to set the tracing, because tracing is a very useful feature. Basically, most of the debuggers have a tracing feature, but I really love it in IDA because it's really simple to set it, and you can really in simply way trace the function calls to all libraries and other stuff. So I want to show you how you can set it to trace all function calls in the libraries, and to be able to highlight all function calls which were executed. So go to the debugger, go to the tracing, and first of all enable function tracing. Go to the debugger, tracing again, and tracing option. You can see that the function tracing is already enabled, and tracing option. First of all, we want, this is the defaultly built-in settings, but we want to trace over library function. You can see the suspend tracing the execution of instruction when IP is moved to a library function. No, we really want to step into the library function to trace all the library calls and other stuffs, to trace the execution to the ntdll.NtCreateFile. So uncheck this, and we can skip loops because we are not interested in loops. And what we want next is we can perform the highlight of the function calls which were executed, but I want to choose another color. Green is better for us, and that's all. This is all settings for tracing the function calls inside the libraries. Okay. We have already set the tracing. We can also show the tracing window, trace window, and put the trace window somewhere here. We are now prepared. Everything is, no, everything not. We can put a breakpoint on the ntdll.NtCreateFile because I want to show you the call stack. So jump to the ntdll.NtCreateFile. How you can manage that? Yeah, go to the modules, go to the ntdll, and filter that, and find the NTCreate file. You can see it here. Jump to it and put a breakpoint here. You can see here is the breakpoint already set in the Anticreate file. Basically, this is the last routine available in the user mode, and this is the call which transfer the execution to the kernel executive subsystem. And this is some value. I will explain it in the last part of this video. Okay, you can see the analysis ended, and we can start to trace. So go to debugger and continue process. You can see that the instruction was already highlighted. Go to the trace window, and you can see that it's running. It's running and tracing all the function calls. From the debug view, you can see, you will see something like, hey, it's not some, it's doing nothing. Yeah, but in the trace window, you can see the trace window is quite exhausted. And what we got here, yeah, you can see that the EIP register or RIP is pointing to the Anticreate file. So we are here on our previously set breakpoint. And what I wanted to show you now is here. What you can see here is the call stack, because you are calling from the main to the Fopen. Basically, what you can see here is something what I show you here. So jump back. And you can see that from the fopen.exe main, it goes to the fopen in a ucrt based DLL. It goes to the sopen s, sopen dispatch, sopen dispatch, sopen no log, wsopen no log, and create file in the kernel 32, and ntdll32 NtCreate file. Here there is missing the kernel base. Create file W. You will see that in the trace window. But this is quite nice. So let's continue the execution because we are here and I want to end in the main function here on our previously set breakpoint. So continue. You can see again in the trace window it's still running and tracing the function calls, and you hit the another breakpoint in the main function. Well, now let's jump to the trace window and we can filter it quite a trace window, modify filters, and as we already saw the stack trace, we are interested in Fopen. Address containing Fopen, and we are also interested in Fopen. We are also interested in create file. And okay, so we filtered the trace window. You can see that only 45 calls were here. So you can see that from the main, it goes to the fopen UCRT base DLL. From the UCRT base fopen, it goes to the sopen. From sopen to the sopen dispatch. From sopen dispatch to the sopen no lock. Sopen no lock to wsopen no lock. From wsopen to the create file w in kernel 32 DLL. And from kernel 32 DLL create file w, it goes to the kernel base, create file w, and from kernel base it goes to the ntdll.dll-NtCreateFile. And this is basically the execution flow to upstream to in the direction to the kernel executive subsystem, and this is basically the path back from the Anticreate file returning to the main fopen function. So that's quite nice. Okay, so we can jump back here and we can go back to our main function. Okay, so jump by name, and we can find the main, and we are on the main. And what I want to show you now, that it's really easy to trace the execution in the graph view because we have all function calls which were executed highlighted in the green with the green color. So jump to the fopen. You can see that the fopen jumps to the fopen UCRT base DLL. If you can't see here the DLL and you are quite lost here, you can switch to the text view and you can see immediately there it's a UCRT based DLL. So switch back to the graph view. You can see that here this call was executed. Jump to it. You can see there are more functions here. What you can see here is a C function which has mangled names, so you can make it more pretty with the option like this options and the mangled names. Show the mangled C++ names as names. Okay, and it's better. What we got next? You can see the command open file. And what we got next? You can see as open s. And you can see as open dispatch again. And what we got next? Here as open no lock. Basically, we can see what we already saw in the trace window. And what is here? W as open no lock. And what we got here? What is here? You can see that here is called to the CreateFile W implementation, so it's a part of kernel 32DLL. Yeah, that's what we are interested in, and you can see that it jumps to the kernel file W implementation, jumps there, and again, if you want to see what library is this a part, so switch to the text view, and you can see it's a part of kernel 32. Go to the graph view and try to find the call to the kernel base create file. You can see it here. It's really nice that you have all blocks highlighted in green, the blocks which were executed, so you don't have to be interested in these blocks which weren't executed. So here's the create file. It jumps to the here, this jumps to the here, and you can see that this jumps to the kernel base create file W implementation, jumps there, and now you are in the kernel base create file W, and here we want to find the NtCreateFile call from to the ntdll. You can see that only these blocks were executed. It's very useful, the tracing feature. So first of all, we can start here, you can start here, and what we got next? Yep, here we can see the execution of a function ntCreateFile, calling the ntCreateFile in the ntdll. So jump to it, and you are here. This is the end of the user mode. And what you can see here, as I already mentioned it, I will come back to it later, you can see some hexadecimal number 52, which goes to the EAX register, and here is some call. Basically, this is call for to wrapper which goes to the sysenter or syscall, and it transfers the execution from the user mode to the kernel's executive subsystem. And this number is very important because it's this number is called system service number, and it specifies the routine which will be performed in the kernel's executive subsystem. And 52 number in hexadecimal, you can use Windows debugger to find out the routine which will be performed in the kernel subsystem, kernel executive subsystem, or you can use this very useful website here, and you can see here that's Windows x86-64 system call table, and basically it will show you what system service number is what function in the kernel executive subsystem. So we are on the Windows 7, and what is important here is one thing I didn't mention. We are debugging 32-bit executable, but we are debugging this executable on a 64-bit processor, 64-bit operation system. So basically, what does it mean? It means that the 32-bit process is some kind of emulated to be runnable on a 64-bit processor, and basically it ends with the syscall calling the kernel executive subsystem, but this number, even this is 32-bit executable, this number is related to the 64-bit processor, because you are in on the 64-bit processor, and the 32-bit process is some kind of emulated. So this is system service number for 64-bit processor and Windows 7. If you jump back to the website, you can see that here is 64-bit system call table, and Windows 7 is here. I'm on service pack 1, and if you scroll a little down and try to find the NTCreate file or number 52 in hexadecimal, NTCreate file, you can see here, and what number is 52 in hexadecimal. So 52 in hexadecimal go to the EAX register, and syscall or sysenter, which transfer the execution to the kernel executive subsystem, knows that we want to perform the NtCreateFile in the kernel executive subsystem, the routine on the routine of NtCreateFile. So jump back to our VM, and that's all. That's all what I wanted to show you. The highlighting features of tracing is very useful, as you already saw. And here is the main. I hope you enjoyed it. I hope I covered what I want. Basically, I want to show you that IDA Free is very powerful too. You don't have to use some leaked version of IDA Pro. Yeah, man, it's as you already saw, the IDA Free version with the support of decompilers is in process. So I hope that it will be something huge. It will help some newcomers in reverse engineering. And I want to show you that the IDA Free has already built in Windows local debugger, which is very useful in many situations. You can learn a lot from that, and IDA has IDA is doing very good job with this kind of features. Okay, thank you for watching, and see you on the part 2, which will be, as I already mentioned, it will be it will be much advanced, and I'll be focusing more on kernel debugging and how we can manage to trace. We will be doing something like this, but for kernel, and how we can manage to trace from user mode to kernel mode, and all with help of Windows Debugger. Thank you for watching, and see you on the part 2.